Our first speaker today is Philipp Saltenberger. Philipp has acquired his PhD in 2019 under supervision of Heike Fassbender at the Technical University of Braunschweig, and he's now working as a postdoc in Braunschweig. He's working in numerical linear algebra, in particular matrix analysis, and today he will be talking about a generic canonical form for J-normal matrices. So, Philipp, please go ahead.
Yeah, thank you very much for the introduction, Marcel. And first, thanks to the organizers for giving me the opportunity to present some of our recent results here. This is work with Ralph de la Cruz from the University of the Philippines, and it's work about a special canonical form for a special type of matrices. So I would like to start with the canonical forms. If you think of a canonical form for matrices that is, on the one hand, as sparse as possible, but on the other hand is revealing all the information about the eigenstructure of a matrix, you probably first think of the Jordan canonical form. So you have the eigenvalues on the main diagonal and some ones above the diagonal. Actually, this form simplifies a lot for almost all matrices, since almost all matrices are actually diagonalizable, so we find a similarity transformation that brings the matrix to diagonal form. Among the matrices that are diagonalizable, there is a special class of matrices, which are the normal matrices. A matrix is called normal if it commutes with its complex conjugate transpose. Whenever we have a relation like this, the matrix is always diagonalizable, and we always find a unitary transformation that brings the matrix to diagonal form. So these are the normal matrices. And the normal matrices are a subject of research for quite some time. So there is a paper from 1987 which lists about 70 equivalent characterizations for normal matrices. So you see these are actually not very normal, but quite special matrices. I would like to talk about J-normal matrices. And these are defined almost like the normal ones. So there's a relation like this, but with respect to a different inner product. And the questions we considered is, how do the J-normal matrices behave with respect to diagonalization, and what canonical form does actually exist for these type of matrices, for these J-normal matrices? So first of all, what is a J-normal matrix? For any non-singular matrix B, we can always define an inner product by mapping two vectors x and y to the complex scalar x conjugate transpose times b times y. This is an inner product. Of course, it's anti-linear in the first component and it's linear in the second component. Here are two particular examples for different choices of the matrix B. So on the left-hand side, you see the choice B equal to the identity matrix, and this gives us the familiar Euclidean scalar product, where just x conjugate transpose times y. On the right-hand side, you see the choice B equal to J, where J is this matrix here. It's a 2n by 2n matrix, so we're in the vector space with dimension 2n here. And it's again x conjugate transpose times this matrix. I would like to call it J times y. This is what I like to call the symplectic inner product. For any inner product and any matrix A, we can always define the adjoint of the matrix A. The adjoint is denoted by A star, and it's the unique matrix that satisfies this equation here for all vectors x and y. And we can calculate the adjoint. It's given by this formula for any inner product like this. When we consider again these two inner products from above, so the Euclidean scalar product, and we calculate the adjoint, we see that the adjoint is simply the conjugate transpose of the matrix. In the symplectic inner product, the adjoint is given by this product of these three matrices. With the adjoint, we are now able to define several classes of matrices. So here is an overview. On the left-hand side, there is again the Euclidean scalar product, and on the right-hand side is the symplectic inner product. Whenever we have a matrix A that is equal to its conjugate transpose, we usually call it a Hermitian matrix. And if we are considering the symplectic inner product, a matrix that is equal to its adjoint is called a skew Hamiltonian matrix. So the skew Hermitian matrices are the ones that are equal to minus their adjoints, and in the symplectic world, these matrices are called Hamiltonian. In a similar way, we have the unitary matrices in the Euclidean world, where the adjoint is equal to the inverse of the matrix, and whenever in the symplectic world the adjoint is equal to the inverse, we call it a symplectic matrix. And last but not least, we have the normal matrices. So in the Euclidean world, these are the ones that commute with their conjugate transpose, and in the symplectic world, the J-normal matrices are the ones that commute with their adjoints. So it's important to note that the Hermitian matrices, the skew Hermitian and the unitary matrices all belong to the class of normal matrices. So they are all normal, and it's the same in the symplectic world. So the skew Hamiltonians, the Hamiltonians and the symplectic matrices all belong to the class of J-normal matrices. So now let's compare the normal matrices and the J-normal matrices. What do they have in common and where do they differ? First, look at the normal matrices. A normal matrix is always diagonalizable, and in addition to that, we can always find a unitary diagonalization of these matrices. So if you're looking for a canonical form for normal matrices under unitary similarity, the diagonal form is certainly the most canonical one for this type of matrices. If you now look at the J-normal matrices, a lot of things turn out to be false here. So the J-normal matrices, or a J-normal matrix, need not be diagonalizable. So there are easy examples of J-normal matrices that are not diagonalizable, and then of course a J-normal matrix need not be symplectically diagonalizable. Since if we consider in the Euclidean world the diagonalization by a unitary transformation, by a unitary similarity, we have to consider in the symplectic world the diagonalization by a symplectic matrix. But this does not always exist here. And finally, there's no canonical form known for these J-normal matrices under symplectic similarity like the form is known for the normal matrices. So our goal was quite simple. Our goal was to find such a canonical form for the J-normal matrices under symplectic similarity. The fact that there is no canonical form up to now does not mean that there is no canonical form for these substructures of matrices. And in fact, there are a lot of decompositions for Hamiltonian, skew Hamiltonian, and symplectic matrices. And here are just a few of them. So, for example, here in the upper left corner, this is called the Hamiltonian Schur form. It's for Hamiltonian matrices. And here in the upper right corner, this is called the symplectic butterfly form. It's for symplectic matrices. Or here in the lower right corner, this is the Page-Van Loon decomposition for skew Hamiltonian matrices. So there are a lot of decompositions for these matrices, and a lot of researchers that have been working on developing these decompositions or developing algorithms that use these decompositions, for example, to solve Hamiltonian eigenvalue problems or to solve symplectic eigenvalue problems. So these decompositions exist. They always exist under certain conditions. And yeah, we would like to consider the J-normal matrices and a canonical form for the J-normal matrices. Remember that they contain the Hamiltonians, the skew Hamiltonians, and the symplectic ones. So I would like to tell you what we found out. So first, recall that a J-normal matrix need not be diagonalizable, and even if it is diagonalizable, it need not be diagonalizable in a symplectic way. So the first thing that we did is to make life a little bit easier and assume that we have a matrix A that is J-normal and diagonalizable. So we have a full set of eigenvectors that is a basis for our complex vector space. And in this situation, we were able to prove the following first little theorem. So whenever we assume we have a J-normal matrix A that is diagonalizable, then we can always find a symplectic matrix so that the similarity transformation with a symplectic matrix brings A to this particular sparse form. So we only have entries on the main diagonal and in the upper right n times n block, and in the lower left n times n block also only entries on the diagonal. This is true for every J-normal matrix that is diagonalizable. It's of course not a canonical decomposition because we have this assumption on the diagonalizability. So how can we proceed here to get a more general statement? The first way is to drop the assumption on the diagonalizability. So this will of course complicate things a lot. We would have to deal with Jordan blocks, with generalized eigenvectors, and things are going to get really hard here. So we decided to go a different way that turned out not so easy as well. We considered our assumption again. So our assumption was that we have a J-normal matrix that is diagonalizable. And we asked the question whether this assumption is actually justified or whether it is exceptional. So if you take a J-normal matrix randomly, will a typical J-normal matrix be diagonalizable or not? So is diagonalizability a standard property for J-normal matrices, or is it more or less a special property for the J-normal matrices? So if you remember the first slide where I said that almost every matrix is diagonalizable in the whole matrix space, there should be some direct reasoning to say that this should be true for the set of J-normal matrices as well. So almost every J-normal matrix is diagonalizable. And we looked for a direct reasoning that this is true, and we did not find one. And I would like to tell you why we believe there is no direct reasoning that tells us that this is true. We can look at the structures that are involved here. So for example, the Hamiltonians and the skew Hamiltonian matrices, they form vector spaces. The symplectic matrices form a matrix group. So multiplying two symplectic matrices will again give you a symplectic matrix. And the set of J-normal matrices, unfortunately, does not have a nice computational structure. So adding two J-normal matrices or multiplying two J-normal matrices will usually not give you a J-normal matrix. So it's just a variety or a manifold. So if we have a vector space of matrices or a matrix group, what can we say about the diagonalizable elements in this space or in this group? And there is no direct reasoning that there are diagonalizable elements at all. Here's a simple example. So consider the set of all the matrices AX, where you have this 2 by 2 matrix and just one parameter X in the lower left corner. All these matrices form a vector space. But this vector space does not contain any diagonalizable matrix at all. And if you take all these matrices and their exponentials, then you have a matrix group. And also in this matrix group, no element at all is a diagonalizable matrix. So there is no direct reasoning why in a vector space of matrices or in a matrix group, there should be diagonalizable matrices. So we had to prove this ourselves. What we first did is we looked at density. So we asked the question whether when we have a J-normal matrix, is it always possible to find a J-normal matrix near the first matrix that is diagonalizable? And yeah, we were able to prove this statement, and this is our next little theorem. So it says that the set of diagonalizable matrices is dense in the set of all the J-normal matrices. So near every J-normal matrix, there is a diagonalizable J-normal matrix. So with this statement, are we able to answer our first question? So our question was the assumption on the diagonalizability of a J-normal matrix. Is this assumption justified or is it exceptional? Is diagonalizability a typical property for J-normal matrices? And to answer this question, I have to tell you what I mean by a typical property, and the term that is usually used in mathematics here is the term generic. And generic is used in more or less two situations. The first situation, it means that a property holds for all elements except a set of measure 0. So this is the measure theoretic approach. Or the second approach is it holds for all elements except a nowhere dense subset. This is the topological approach. To say that the diagonalizability is a generic property, we should prove that the complement of this set is a nowhere dense subset. The complement of a nowhere dense subset is a set which is dense, which we know the diagonalizable matrices are, and which is open. And this is the property that we're still missing. So this leads us to the question, if the set of diagonalizable matrices in the set of the J-normal ones is an open set. And this, unfortunately, is not true. So this set is not open, and we have a problem here. But we solved this problem by looking at a slightly different set of matrices, which is contained in the diagonalizable matrices. So what we did is we looked at the J-normal matrices with 2n distinct eigenvalues. Of course, a matrix with 2n distinct eigenvalues will be diagonalizable. And for this set, the statement, in fact, is true. And this is our next little theorem, that the set of matrices with pairwise distinct eigenvalues is open and dense in the set of all the J-normal matrices. So this means that the complement of this set is a nowhere dense subset. And this brings us to our final result, to our final theorem, that for all J-normal matrices except a nowhere dense subset, there always exists a symplectic matrix, so that the symplectic similarity transformation brings the matrix to this particular canonical form. So let's compare this with the things from the first slide. On the first slide, I had the Jordan form, and I told you that almost all matrices are actually diagonalizable. So we do not need the Jordan form. Almost every matrix can be brought to diagonal form by a similarity. And now the statement for the J-normal matrices, we were not able to prove general canonical form. That is, that we can have for every J-normal matrix, but we have the statement that almost all J-normal matrices can be brought to this particular sparse canonical form by a symplectic similarity transformation. So with these results, I would like to conclude. We began with the normal matrices. The normal matrices are always diagonalizable, and they are always unitarily diagonalizable. So we find a unitary similarity transformation to diagonal form. Then we looked at the J-normal matrices and have proved that the set of diagonalizable matrices is dense in the set of J-normal matrices. And this was not quite enough to prove that our canonical form is generic. So we looked at the set of matrices with pairwise distinct eigenvalues, and we were able to prove that this set in the J-normal ones is open and dense. So its complement is a nowhere dense subset, and we can now say that the canonical form is generic for the J-normal matrices. So the J-normal matrices have a generic canonical form under symplectic similarity that looks like this. What future work? Future work is, of course, to find a way to compute this canonical form in an efficient way. So this is still on our list. And with these results, I would like to conclude my talk, and I would like to thank you very much for your attention.
Thank you, Philip, for the great talk. This was a really interesting topic, and I hope that we have questions on this. So, Catherine, do you have a question for Philip on Zoom?
Yes, we do. So Caroline Penke asks, are there situations where J-normal matrices show up that are not skew Hamiltonian or symplectic? There
are few situations. So the skew Hamiltonians, the Hamiltonians, and the symplectic matrices are, this is the vast majority of situations where these matrices show up. The J-normal ones, few situations, but not so much. Yeah.
And we have one more question from Daniel Kresne. Why is it difficult to compute the normal form?
We haven't computed it yet, so this is on our list. So to prove this, that this canonical form does exist for the J-normal matrices, works actually by splitting a J-normal matrix into its Hamiltonian and its skew Hamiltonian part, and then we puzzled everything together so that that we end up with this form. It's not an efficient way to compute this form. It could be done, of course, but it's not efficiently. And yeah, we are looking for an efficient way to compute this form.
Okay, Davide, do we have further questions in the YouTube chat?
We don't have any further question. There's just a comment by Clive Moller that say, beautiful talk, thanks.
We do have one more question on Zoom if we have time.
Yeah, I guess so.
So Frank Ulig asks, why did you change the standard notation of A star to AH and then use the old classical definition of Hermitian transpose A star by AH?
So the H is just, I used the H just to denote the complex conjugate transpose. So of course, in the Euclidean scalar product, the star is simply the H, and in the symplectic world, the star is something different, where the A appears with the H here in the middle of these two matrices. I hope this answers the question.
Okay, I guess we should switch to our second speaker now.